I don't even know. Does anyone use these? It's so hard to see anything on the video.
Okay,
All the time.
The audio's nice?
Yeah.
Okay, use the audio. You use it? Don't lie to me. Why would you do that to my poor heart? Right. Any questions before we get started today? I'll hide yourself. Let me hide you so that we do the view properly. No. Hide non-participant video. Hide selfie. I don't understand how to do this. Immersive? Oh, no, we don't want to do that. Oh, God. There we go. There
Well, we still have 2 minutes.
I know. Did you have any questions before we get started? Actually, I only have 1 minute.
I don't think so.
Oh my God. See, they stole the good one. Thief of joy. Oh my God, I'm gonna kill him. All right, hold on. Let me get the better one downstairs.
Oh,
Now I'm gonna be late. Watch this. Criminal.
Oh, it's probably just nice hanging down the door. Coffee of the day. Freshman grades.
I gotta be busy.
You're gonna be losing?
No, I can't, but I can't.
Why not?
Needed.
Breakfast sandwich. Bagels and sugar, squeezers. This was dark cheese.
Oh, this panda open. Panda.
Oh, my God, seriously.
Building.
You sure?
That's not showing. Yeah.
You're back. No. Holy shit. Wow.
All right, ready? There we go. Last questions about electrostatics and matter. Go. Yeah, anything else before we, we're gonna move away from it now. We're gonna talk about magnetostatics and matter. So this is your leg. Last question time.
Oh, can we go to the E naught, ER, E?
So you yeah.
It's that.
Yeah.
Explain how we go.
So this is the relative
Okay.
permittivity. This is the permittivity of free space. As if there's nothing there. And this is the one for the material. So these really are the same type of thing. They're just multiplied by this constant. This is a constant that we find in nature. These are property materials.
So when do we know to use ER versus E?
That's up to you,
Oh, okay.
right? You know, these are constant details.
Okay.
So sometimes you'll see, and we write it in terms of this, because you'll have something like the relationship between D and E, right? So the way that they're proportional uses this. So if you're thinking in your head, how does one impact the other? It's through that proportionality. This, right?
So we use R for that.
Oh, you tell me. Look, right. It's in the notes.
Yeah.
Okay. Yeah.
About displacement, I'm still a bit confused about what exactly it means.
Okay. What does it mean, folks? Yeah.
Is it?
Say that again. Polarization of the electric field.
Polarization and
Yeah, but what does it mean? Right, you're right that that's exactly what it is. Yeah,
It's the electric field and then also what happens to the electric field?
due to, yep, you're almost there,
Polarization.
due to the material that it's impacting, right? So it's the original electric field. But then in real life, there's materials that it's interacting with, and those materials can polarize. They generate their own electric fields, which add or subtract from the original electric field, right? Generally speaking. Okay,
Okay.
cool. All right. Magnetostatics, just in a nutshell. Okay. You have some charge. We're gonna imagine that we're moving, charge is moving with a constant velocity, so let's take some charge here. Q. Okay. They're gonna create magnetic fields. All right. What are the forces that this thing feels? Potentially from electrostatics and magnetostatics.
Electric field.
Electric field, so that is written how?
You-
Q E. Anything else?
What about the,
Magnetic forces, good. What are those?
oh,
V cross B. Okay. This will be important because this is proportional. So this speeds the object up or slows it down. And what does this do to the motion?
curve.
Good. Spin it right round, okay? So the motion together does what to an object? A charged particle moving in an electric and magnetic field
Like curls around.
moves like a helix, right? So it does this, spirals. Okay. So at rest, the charge will feel an acceleration. Okay, and then it accelerates, it feels the B field. It curves it, so let's look at this little picture here. Let's imagine that B is going this way. Let's say E is going this way. Let's start a particle here. And it's gonna make these fun little loops. Okay. So at rest, it feels E. Starts to pick up speed, but is deflected by B, right? Until it slows down to a rest, and then it starts again, right? Fun, right? So the orientation of the magnetic field is really important because you can arrest motion with it, you can stop it, or you can make it curve. All right, what if you do something like this? Let's say you have a box and there's some charge here with an initial velocity v. Maybe you've seen this already, say at the beginning of the semester. Okay, now it comes in here. Let's say there's b into the board or out of the board. What is the particle do? Goes up or down depending on whether it's in or out, right? So it's just going to curve, right? And then maybe it leaves and it's going to go straight in. That makes sense? The radius of curvature you've calculated before. This is how we do something called mass spectrometry. What we do is we send some particle in, depending on how big it is, you can separate it by mass and charge. So larger mass, smaller charge, etc., will curve you more or less. And then you just have little boxes that you collect the particles in. Okay. Let's talk about the continuity equation for magnetostatics. So you've seen something like this, I hope. What does that mean? Is it charge density? Current density, good, good, good. Okay, and that's equal to what? Yeah, there's definitely a rho. Let's think about what the word current density means. The rho dt. What does that mean? Rho is the charge density, and ddt is the rate of.
Yeah.
So the rate of charge density is the current by definition. Right, so the divergence of the current is due to the rate of change in the charge density. Right? So this means that I'm going to generate currents if I'm either adding charge to a region or I'm taking it away. If the total charge isn't changing, then there aren't currents. Right? Make sense? Okay. Usually we require steady currents. So sometimes we'll say something like this. Right? And then you get a fun thing called the PHYS law. It's just as fun to understand as it is to say. All right, what's the PHYS law? Intellectually. Yeah.
Yeah.
The total contribution of magnetic field. Say that again.
The total contribution field on
Right. So basically what you're saying there is, how do we generate the magnetic field everywhere? Well, that's due to the fact that every little piece of current, okay, contributes along a line. Okay. This one here. That's the current, not the current density, that's just the current. This one here, only valid to be pulled out of the integral. In magnetostatics, right? But because if it varies along the line, then you can't pull it out of the integral. So that's straightforward. So intellectually, when you think about the PHYS law, it's the same thing as the Coulomb law. You're grabbing the contribution from every piece of charge with Coulomb's law, and then you integrate it. With PHYS law, you're grabbing the contribution from every single piece of the current flowing inside a wire or flowing wherever it is, and you're summing them up to get the magnetic field everywhere. Okay. You've seen Ampere's law? This is that the surface integral of BDL is simply mu naught I. Okay. This is coming from Maxwell's equations. We can use these together to get one more thing. So we can say with Stokes' law that E DL, okay, equal to the integral over a surface of the curl of E over that surface. Do you remember this? When did I use this?
Specifically the curl of B or just like the general.
Stokes' law. Oh, this is Stokes' theorem?
Yeah.
What? Perhaps, but the first time I used this was in fluids. I know you've all deleted that from your memory, but it turns out that these things are necessary. We're talking about continuum mechanics here. Except the continuum we're looking at is a field formalism. Okay, we haven't discussed what a field is yet, intellectually, but we're about to get there. But to understand how these continuous things work, we have to use some of these tools. So here's Stokes' theorem, which is relating the dot product of B to the curl through a surface, right? We write something along the lines of, here's I is J dot dA. Okay, that's the flux. Right. So therefore we can write something like this. Okay. So another way of writing that is that del cross B is equal to mu naught J. Okay, this is Ampere's law. And what does that say? That says that the curl of the magnetic field is coming from the current density. Everyone's remembering this now, right?
Were you able just to get rid of the integral and dA on both?
Yeah, because they're both dA integrals.
So you guys get rid of it?
Yeah.
Okay.
Well, it's not that you're getting rid of it. It's if you're taking an integral over the same area, right?
Uh-huh.
And they're equal, then by definition, the integrands have to be equal. Right? If this was a line area or a line integral, then this wouldn't be the case.
Okay.
But since you're integrating over the same surface, then the quantities have to be the same surface. Right? Okay. Let's think about this a little bit more, because I know everyone's brain on a Thursday is broken, right? So let's do an idea here. Let's take some current like this. Here's the distance A. This isn't going to be an infinitely long current. Okay, so this is infinitely large. Okay. I is going to be evenly distributed along this current surface here, around this area here. And we're going to draw an Amperian loop around the outside. Okay. So first question here that you want to ask yourself, wake your brain up in the morning. Can we use Ampere's law here? Think about it, discuss it with a friend.
Where we could.
Can we use the Ampere's law on that?
Yeah. Oh,
No, sorry.
Which one was Ampere's law? Top one? The bottom. Oh.
this is the derivation of Ampere's law.
Oh, derivation.
If it's infinitely long, wouldn't
Yeah.
it have the same,
Yeah,
Uh,
I appreciate it.
what is it called? Magnetic field? And therefore there would be no curl. So it would be-
What are you saying that the magnetic field is zero?
No, because, I mean, if there's current, there's a magnetic field, right?
Okay, so we know there's a magnetic field here, right? Everyone agrees.
Yeah.
And how will it look?
Not
That.
clockwise.
What about inside?
Oh,
If we looked inside,
wouldn't it be dependent on it?
we're gonna think about both of these things. All right, let's imagine how we would use this. What's the direction of B?
Where?
What?
Where?
It's curling around.
You just showed, me, right?
Yeah,
Yeah.
like where do you?
In this Amperian loop here.
Oh, well,
Sorry.
Out of board on the left.
So I is going this way,
Yeah. I'm doing that.
and phi is this way.
Yeah.
So we can use something like phi that's going in this direction. Okay, good. Okay, so if we use this formalism here, okay, we have a I, we can find B. These are the same statements, right? Everything in here is consistent. Okay. So what's DL?
The infinitesimal like length of the period loop
Yeah, and which direction is that?
in the phi direction.
In the phi direction, so DL really is
D phi.
S D phi
Oh, S.
in the phi direction. No? Yeah, okay, what about B? Well, we're just gonna break this down, we're gonna say that there's only one B component here. Right, B phi in the phi direction. Well, that's good, because those dot products work. Awesome. And so we can write something along the lines of the integral of B phi DL all the way around is going to be equal to mu naught I enclosed. What's the integral all around of the constant?
All our constant times.
YouTube pi.
2 pi.
Oh,
It's SA.
oh yeah,
Where's, did you say it's SA?
Yeah,
Well, S is a line, right? This is the distance to S.
hmm,
Outside of A. This Amperian loop is outside of A. 2 pi S squared. All right, let's do this integral. Okay, B naught, B phi comes out, right?
yeah,
What's DL?
S D phi.
S D phi.
What coordinate system are you using?
Cylindrical.
Oh. Okay.
Why?
That just tripped me out that you put the S like diagonal.
Oh, okay, let's do it like this.
Yeah, okay, nice.
Very good, thanks. Nice catch. Okay, so this will be your S then. It goes outside of A. S is larger than A. Okay, does that help?
Yeah.
Okay. Sorry, Isabel. All right, so now this. Is S dependent on phi?
No,
Okay, so that comes out too. What's the integral of phi?
pi.
2 pi, very good. Okay, so where's this pi r squared stuff, okay? This is a line integral, we're going around in a circle. That's the circumference of a circle, no?
Mhm.
Oh, okay, that's okay. And what's the sequence one?
Hmm,
You're not iron close. So now we have a formalism for B, and this is how we do these derivations in the first place. And you get this fun thing in your 2500 book, which is just mu naught over 2 pi S I. Okay. So how does this look outside of our long wire? So we all have the right idea that it curls around, but how does it decrease as a function of radius? So most wires, you do not feel magnetically attracted to, right? When do you feel attracted to them?
when you're really close to it.
When you're close, because they fall off as 1 over S, right? Okay. Okay, so that's outside. We could do inside too. You want to do inside?
Sure.
Okay. You want to do inside?
How is it gonna be?
You tell me.
So the S is net?
No, you tell me. You're gonna write it down right now. You're gonna do inside.
Okay,
So turn to a friend, start writing down how you would do inside, and we'll see if we get the same thing. Where's the paper?
Oh, I was thinking.
Oh, you can't do anything without paper.
Yeah, but I think I don't think it's close, it's just because the whole thing's. Yeah, I don't. know what that kind of feel. They're magnetic field. Oh, no, I can't do it. Is there a magnetic field inside a wire?
I don't know, you tell me, what is this part sense? How do we interpret this statement? BDL,
Over a closed loop.
magnetic field over a loop, a closed loop,
Yeah.
is only due to
If not.
enclosed.
Yeah.
Okay. So just like we thought about with charges, this is not unique. Right? This is not something brand new. The fact that any loop encloses charge generates
Mhm.
an electric field. The fact that any loop encloses current generates
Okay.
magnetic field. Good. You see the similarity there?
Mhm.
So you had some Gaussian surface and you have, some sphere and you have a positive and a negative. Right? So you have just as many things going out as coming in, no E field outside. You have a single positive charge, the presence of electric charge. Now you have an E field. Here, if I had two loops, one going down, one going up, such that the total current was 0, do I have a magnetic field?
Mhm.
No. So let's have a look here inside of this wire. As I start at the surface, do I have a magnetic field?
Yeah.
Yes. At the surface, you certainly do.
Mhm.
And as I go into it, do I have a magnetic field?
Going through it. right?
Yeah, there's less.
Yeah, it has to, right? Say that again. You're almost there.
The current is decreasing because the.
Right, so there is a function of the surface area. So because you have uniform current in the area, as I shrink that current circle down, right, as my loop gets smaller, the current in that loop will start to go to 0,
Mhm.
right?
But are you saying like the current is coming out of all ways? from the pump?
Yeah, so we just imagine that this whole, it's an infinitely long wire. And there's a uniform amount of current going through the whole thing.
Yeah.
So outside, we saw how it decreased. It decreased like 1/s. And certainly at the edge, it has a value. It doesn't go to 0. And as we go into it, the amount of current is going to start to drop. So I have an expectation when I go to write this up, one, that there is a magnetic field inside of the wire, and that as S approaches 0, the magnetic field should go to 0. So let's see if we can prove that. Can you prove that? No, he said no to me. Say that again?
We just replace I with the interval with J dot V A.
Yeah, we could do it even more simply than that. If we think that this is uniform,
We assume that is uniform current?
Yeah.
And it's just current will be-
so this is I enclosed, right? Maybe I'll be specific here. Is there a relationship between I enclosed, S and A?
I something. Do you think of ratio of?
Hmm.
Can you explain that again?
Which one?
The magnetic field inside.
You want me to talk about the magnetic field inside?
Yeah, can you explain that again?
Yeah, okay, so let's imagine we have this situation. We have a wire. Okay, here's the wire. Okay. inside is material. And there's a current all uniformly moving upwards. And now I take a small subsection around the core. This is my Gaussian circle. Okay, how much of this current is enclosed compared to this?
Blockness.
How much? Right, this is the quantitative part. By what fraction? By what amount?
You make like a B, like, or like any variable, I guess. And just have like the actual area of A divided by the other area of A, and then kind of like subtract them.
So you'll see the hint that I wrote on the board. One is over the other, not minus the other. Right?
Which is A over the new one.
A over the new one,
Yeah.
S over A. That's the quantity that you want to use when you compare this size to this size? No.
No, it's not.
No.
Because S's are on the outside. Then we want to just compare what the actual current density is of A with the new density inside.
Okay, yeah, so but what's the relationship?
Right.
You do know how to write it. Is this shape the same as this shape? And if so, how? What's that?
Same.
Is it just S over, right?
Is it S over A?
A
Is
over
this length the same as that length? Compared to, is this shape the same as this shape? Why am I writing the shape?
Oh, 2 bar.
Yes, why? Because it's an area. We're comparing areas of a circle. You're not comparing the length along the edge. You're asking how much material is going through an area, right? This is the area it's going through. It didn't matter before because it was just I. But as we get to the edge, you need a relationship that compares, depending at a certain distance S, how close you are either to the middle or to the bottom. And it does not scale linearly. It squares quadratically because the area is quadratic. You see? All right, so let's write this properly. I enclosed is what? On the top, what do I put on the top?
Or sorry, by S,
I'm gonna do pi. Pi s,
by squared.
pi s squared again, the right units here. And on the bottom,
Squared.
pi a squared, very good. All right, so that's great. So now I enclosed has a fun relationship. I enclosed is simply the total current times
That's where we're.
S over a squared, good. Done. Does this have the right form? Let's check the limits. When S is 0, what's the I enclosed? Good. Does it ever go to infinity?
No.
No, good. So we didn't accidentally put S on the bottom, which I've been known to do many times in my life. Okay. So S needs to be on the top, so this goes to 0. And when S is A, what do we get? I enclosed, good. Okay, so what's B?
You want like the final answer?
Excuse me?
You want the final answer like the next?
Probably want the next thing.
Probably not.
Oh, it's- that's-
Wait, cause I kind of have a final answer. Oh, wait, give me a second. No, we're good.
Yeah,
Could we just place I enclosed on that one? With this,
you tell me.
that's what I would think you did.
You would just grab this last answer here.
Yeah, we just replace the I with this new stuff.
Anyone disagree with that? Is the geometry different at all?
No, this is.
Still certain.
Still circle?
I did it like actually like integrating like, or like, yeah, with integrating B and you know, PHYS, PHY.
You just did this and you
Yeah,
got that,
I
right?
redid the steps, yeah,
And you got the same thing, right?
yeah.
Okay, so in fact, you do see that it's kind of similar, right? So you don't have any expectations that it should change direction,
Mhm.
right? It's not going to suddenly go tangentially to the way it was going before. So you're saying, let's just replace it. That's fine with me. But you walked through this process, right? You didn't just look at the end and say, that's the only thing I have.
No.
Okay, good. So let's do that then. So B inside started as what? Mu naught over 2 pi s, I enclosed. And what's I enclosed now? S over A squared. Oh, yeah. Okay, good. I drew it really well. Okay, so what does this go like?
Mu naught I times S over 2 pi a squared.
Okay, interesting.
It's so sick.
So what does B look like as a function of S?
That's increases.
It's the line from 0 to 1.
From 0 to 1?
Yeah. From 0 to
Exponential.
something,
To what?
you know, I. um,
0 to A, right?
When
When S is an A.
Well, I'm not, I see the B value.
Oh, you're right. The B value, yeah, I don't care what the B value. I just care about what the feeling is, right? So it increases linearly inside the wire and then what?
Then 1 over all.
Then 1 over R.
Oh, so it doesn't just die off.
Well, it dies off after 1 over A.
No, I thought at A it just dropped 0.
Why would it do that?
Because the way you wrote it, it looked like. it didn't.
Oh, sorry, let's do this. My bad. There you go, that's the point A. Okay. Okay, so now we understand wires. We've all woken up the magnetostatics part of our brain, yeah? Let's talk about vector potentials. What can I delete? Can I delete everything?
Yeah.
Is there so much hair in this eraser? It's gross. All right. Words. All right. What's a vector potential? Where's the book? Gotta read the book before we come to class. That's what I'm asking. Vector potential. All right. You've seen scalar potentials. What's a scalar potential? What is a potential?
Energy density.
Okay, yeah, so like potential energy, you've seen that before. For our class, you would be talking about voltage, yeah, you'd be talking about the V potential,
Yeah.
right? And how would you write that?
For like a single charge or
Yeah, let's say I want to relate E to V.
negative gradient.
Negative gradient. Okay, this is really the negative gradient, not the integral. Okay. What is this? Is that right? Is this correct?
No, actually, no, there's no.
No, it's wrong. In fact, there is no vector on V.
Hmm.
What?
There.
That's because this is not a vector quantity,
The scale.
it's a scalar, hence the word scalar potential. All right. V here is unique. Special little snowflake. What about for B?
With the negative gradient of A there.
Okay.
What is in that? What was the magnetic potential?
I did like the letter A.
Oh, I think it was a curl of A.
Ah, the curl of A. In fact, that's why we call it the vector potential. Because you are doing a curl of this. So is A scalar or vector? Raise your hand for scalar. Raise your hand for vector. Yeah, in fact, it's vector because it's called the vector potential. All right, good. It's okay. It's not meant to be a gotcha, but we're trying to keep everyone on their toes here, right? Okay. This, however, is not unique. And this is gonna be the bane of our existence. Okay? So you hated electrostatics. Get ready to hate something even more. Ready? All right. Let's say we know B first. We find B, and I want to find A from this formalism. Okay? Let's imagine a world in which B. Let's imagine a world in which B is simply in the Z direction. Okay? What is del cross A? How do I break this up?
It was all like the partial and final.
Yeah, you need to, okay, I see like hand motions and,
Three main.
just show me now, which ones are which?
Do the matrix.
Things minus each other, okay.
Do the matrix.
Yeah, just do the matrix.
No.
No,
You
no,
have to remember what the hell it is.
no.
Oh, okay, alright, so the top,
Oh, X hat.
X hat, good,
Yeah.
good,
Yes, yeah.
good, alright, we can do it together, and this one?
Yeah,
But
yeah,
yes.
yeah.
Dx,
Yeah.
Yeah,
dy,
Z,
dz, good. And this one?
AX.
Oh, we can do it, okay, and everyone hated it, and yeah, everyone knows how to do it, okay, and then so what is it?
Shit, it's like crosses on.
Oh, I know
What? Okay, right, equals?
Is it like J?
Az dy?
Yeah.
No,
DY.
dy az.
Yeah.
It's important that we do it right though, right? Because these are not communicable operators necessarily,
Oh,
Yeah.
right?
Yeah,
If you
so-
flip them, then you get a negative sign.
It was
Okay,
DY is.
in the X hat there.
So d dy az
Minus
minus, very good.
DY AY. DY.
Oh, I wrote Z.
Oh,
GG.
Good, thank you for catching it. Okay.
easy. AY.
Okay, so let's stop and look at this for a moment. So this is what? X hat? Okay, and so this has to be equal to what, given our situation?
Zero.
0. Okay. Next. What?
Yeah.
All right.
Yeah.
Ah, it's the other way around because it's a minus, right?
What?
Yeah, there's a negative.
What's that?
There's a negative in front of that term.
Oh, do it like that.
Yeah.
Okay, it'll be fine. We're gonna notice something very quickly here. The next one?
Minus
Minus.
AZ or GZ AX.
Okay, and this is y hat? What's that equal to?
0.
Oh, crap. So it doesn't matter that that's there, I don't care, because I can just multiply that. All right. So, good, next,
How are you erasing the X and Y?
because I'm writing a system of equations.
Oh. Now it's dx, say what?
So dx
A what?
ay
Minus
minus,
dy is equal ax, right? dy. Ax.
and that's the z hat one, right? That's equal to? Oh, that is equal to something now. B. Okay. So if you look at something like this, you will get frustrated, right? Because how many unknowns do we have? 4 unknowns?
Sorry.
3. We're gonna assume that I gave you B, right? Like B is like 4 or 16 or something, right?
Okay.
And I asked you to find A. So now you're given 3 equations, 3 unknowns, are you good? Well, you think so,
Yeah, no.
but you're not. Okay, so let me show you why this gets annoying quickly. So these are not unique because this is the curl of a single function, the vector potential. So let's do some examples, right? Let's think up some fun ones. All right. Let's first start with ax equals 0. Then ay, right? Multiple solutions, let's start with 1. Ax equals 0. This is 0. So what's ay?
Oh, b.
Not just b. Taking the derivative of x.
Oh, b times x.
B times x.
Oh.
So then by definition, ay has to be bx, right? Okay, so what does that look like? That's okay, let's draw this here. So here's x, here's y. What does that look like? Yeah, good, like that. And anything else?
Oh, yeah.
Okay, there's the negative solution, and so ay, or sorry, a looks like this, right? And then in this location, it looks like that,
Oh, never mind.
because it's a vector quantity, right? Ax is 0, ay is simply bx times that. Right? That's one solution, and that fits. Does it fit the other ones? Try this one here. Az, let's assume that's 0. Ay, not a function of z, so that's 0.
Oh, okay.
So that's 0.
That fits.
This one, az, 0. Ax, 0. So that fits. Oh, okay. Good, we figured it out, right?
Totally.
No, your greatest nightmare. So let's look at 2. Is there any other way to write this?
Ay, 0.
Yeah, make ay 0, right? And so now ax is gonna be b times y, right? And this is just going to be flipped. Okay. Correct? Okay, so non-unique solution. Do you have any more?
Thank you.
In fact, you do have one more. It's fairly straightforward. So what we did before is we just made this like fun game where we got rid of one, but can we actually make them add up to b?
Yeah.
Yeah, you could. You can make this one 1/2 b, this one 1/2 b with the things getting rid of each other, and then they would add to b. right? And you could do that simply with this. AX is 1/2 B times Y. And AY is 1/2 B times X. Right?
Why do you even negative?
So that the negatives cancel and they add to B.
Okay.
Right? But what does this one look like? So if this is your vector quantity, A, X and Y like this, you get a circle. Try it out, right? So B, let's say this is 0, then AX is 0, and this is non-zero, so it's out here. And then as it goes up, it goes around. That. And then this one goes up and around like that. Right? You see it or no? It's a parametric equation essentially. You remember those from coding them? Okay. Just go around the circle. Because this one here, A, is a vector quantity. So this is AX dx. And so the thing is being traced out. Right. So this essentially here shows that A is not unique. Okay, here's the front of your book. Here's your scalar potential due to charge. Here's your vector potential. Notice the little squiggly on the top. Due to current, not unique. Okay. How are we feeling about that? You want to see examples of A, or can we move on to magnetism? What does that mean? Move on. Raise your hand for move on. Magnetism. All right. Then we're gonna skip these examples. We can do them in the student help session. There's just 3 more pages.
No.
I don't have one planned, but if you need one, we can talk. Okay, we ready to talk about magnetism? What's the famous magnetism line?
Oh. You're saying.
Insane Clown Posse?
I like that.
Do you know Insane Clown Posse? Okay, your homework, should you choose to accept it, is Magic is Everywhere by Insane Clown Posse. Hysterical. Watch the music video and you will see there's a magnetism line. And when you see the magnetism line, you'll be like, okay, I get it. It's probably before you guys are on the internet, but that's okay. Okay. And anyone familiar with magnetism? Yeah, give me an example of magnetism. Magnets, good, thanks. Helpful. Loud beads that slam together, the Bucky beads. Okay, anything else?
I was gonna say,
Computer tops, right? Lids.
I was gonna say.
Oh, yeah.
Ferromagnetism.
The memory thing. You have experience with that?
I've heard about it.
Okay. Yeah, you can wipe them.
Yeah. Oh, what are those called? What the hell, like the thing? It's all remember.
Is that it? Anything else?
They're like those games on the pens.
What?
Those scratch board?
Terra.
I have no idea. We'll get
It's,
voice.
it's materials that when you put them in a electric field, magnetic field, they gain. It goes back to one.
What?
Ferroelectric.
Ferroelectric. Okay, so we heard a lot of good words. We had paramagnetism. I heard ferromagnetism. What is magnetism?
Isn't it just the fields
Something
resulting,
like polarity?
fields resulting from moving electric charge?
Right. So we know that magnetism is caused by moving electric charges. So in practice, let's assume that this is a giant magnet. Use your imagination. How far wide is this magnet?
Because the atoms inside of the magnet have like little dipole moments and they're all aligned.
Okay, so I like a lot of those words. A lot of those words. Dipole moment, atoms, right? Magnetism is an emergent phenomenon. meaning that we see it due to the motions of individual electrons moving around, right? So these individual electrons move around, they generate what is essentially a current, right? Current density. That change in current density can generate magnetic fields. Now, in a lot of material, this is in fact not magnetic. I was lying, right? So why is this not magnetic? Yeah, but why is this not magnetic? You just said it's a property of metals. I'm not asking about metals. Why is this not magnetic?
Because all the dipole moments are in random directions at all.
Ah, okay. So even though this thing, right, has atoms inside of it, all of them are randomly oriented. So what is special about a metal? Yeah, depending on the type of metal, right, it can either reorient itself or it was created with an orientation. Right? What's that? What? Okay. All right, so let's talk about magnetism. We're on chapter 6 now. And we're never going back. Just go back. All right. All right. So the concept is very similar to polarization, but it's not quite the same, and we're going to see some of the major differences. Let's just say we apply a magnetic field, right? Here's some B field. You're going to have individual electrons. Here's your plus, and here's your minus. Oh, okay, let's try this better. Minus Q, plus Q. And let's imagine that it's going around in a circle. This is obviously a mental model. There is not an orbiting electron in a circle, right? Okay.
What is the big one inside?
What?
What is that?
This is my negative charge. And this is my positive charge, and then this is my loop. Okay. And because the electron's going around, moving, a moving charge is a current, right? So this is I. And now that I have a moving I have a contribution to this B field. Right? Boom, that's how we generate it. You saw that from VO Spark. Some distance, I, right? Bada bing, bada boom. Okay. You have a magnetic dipole. It's different than the electric dipole for atoms and molecules. Generally speaking, electrons spin as well in opposing pairs. And you tend to have, let's see, magnetic materials tend to have odd number of electrons. So when you look, there's a, I think it's the fourth problem in this chapter. It like literally gives you different materials and asks you which one do you expect to be magnetic based on how many extra electrons there are. So the reason why you might look at something like this and you say, well, there's just one. Okay, no big deal. If you have something like helium, right? Here's 2 positive charges. And then here's 1 electron, Q minus. Okay, that's going around this way. This is not really going around that way, but you know what I'm saying? And then you have another one over here that's going around the other way. Now you already see an immediate problem. They don't actually hit each other because they're not actually doing that. But this is like how we think about it. They are in fact rotating in opposite ways such that their magnetic moment disappears. So is helium a good magnet?
No.
No, of course, you already knew that. But let's look behind you. Which ones might be good magnets? The one that's metal. Okay, thank you, folks. What about helium? Oh, sorry. What about iron structure? There tells us that it's a good metal.
The number of valence electrons that are in there?
Right, valence electrons, right? And does it have odd valence electrons? So if you look at the one next to it, manganese, is that a really good magnet? Mangan? No, just trying to trick you. No, I was trying to trick you. And in fact, it's not a good conductor. What's that?
Like cut really easy.
Wait, why?
I don't know.
that's magnesium. Just kidding.
Magnesium you can cut easy. Okay.
Why?
Wait, electrons go in opposite directions.
Not really. They do, but not really. So remember that we don't see electrons, right? We're talking about quantum mechanical objects. They are not billiard balls. So this electron is just a mental model of a physical object that our brains simply cannot fully comprehend. You'll probably need 3 more years to fully dissociate from the idea that the electron is a real thing. Because it's a point particle, right? And it moves around, it has an orbit, but it's a probability cloud. So it's not really in a location going around in a circle. It's the probability cloud is spinning. And so these two probability clouds, they don't care about each other, right? They are both present. They're doing this. One's rotating this way, one's rotating the other way. More or less. That's a bad analogy too. Because I'm trying to use terms that we can physically understand. And we're talking about a world in which we have no experience. None of you have ever spent time in the quantum realm, despite what Marvel will try to have you say, right?
Why don't we even teach us like that?
What do you mean?
Like that, like there's one thing that spins this way.
Because it acts the same way,
Um,
right? You won't notice a difference here until you start to ask Kobe's question. Wait, one is spinning the way that, why don't they hit each other? Because that's where we break down our mental model, right? We break down our mental model because we really think of them as particles being able to hit each other. They will scatter off each other, and you'll do quantum mechanics that shows that their wave functions interact, but they can be simultaneous, right? There's this wonderful, I can't get on this topic right now. There's a theory that there's not individual electrons, that they're all one electron moving through space and time. You can show it, it is not wrong, but it's dumb, right? Okay. There's a couple words that I heard as well. I heard diamagnetism, I heard ferromagnetism. Anything else? There's a third one maybe?
It's a ferro.
Ferro. Let's write them down. What?
is there PHYS?
No. That's smart though. That's different. Okay, ferro means what?
Metal.
Yes, okay. Ferromagnetism means iron magnetism. Good. Okay, you're very close. You're very close, very good. Okay, so it retains the magnetic field even after the magnetic field that created it is gone. Right, these are your inherent magnets, the ones that retain that sense of magnetic polarizability, right? Okay. So they retain B after is hysteresis. Nothing about that yet. Okay. What's the next one? Okay. Which one is which?
Paramagnets, they don't retain their magnetic fields after it's leaves the field.
Uh-huh.
So it can orientate, and then once it immediately after it leaves, it goes back to random. Back to normal.
So a different way of saying this, right? These are both, like you just said, they don't retain that. So I look at para as parallel, and I look at dia as opposed to. So all I'm talking about here is the orientation with respect to the original field. So this will be parallel to the original field, right? And this will be perpendicular. Or anti-parallel. Okay. What's the example of a diamond? I don't know.
Oh.
I don't care. I told you that the stuff in materials doesn't do anything for me. The way that light interacts with materials, oh, awesome. Okay. And in fact, the different we'll talk about this more when we think about the way that something like an electron or an atom has energy based on its ability to have these charged states. So you'll notice, for example, that maybe you've talked about this already in quantum mechanics. You have some electron spin, or you have the orbital, and then you have multiple, and you have one state. You calculate the energy for that state. And then you stick it in a magnetic field, and it's going to split the state. So now the presence in the magnetic field means that it will use its inherent magnetic moment to create one that is aligned with the state, anti-aligned with the state, and they'll have different energies. So this is how we see magnetic fields in stuff really far away, like stars. We see individual atoms in a strong magnetic field will have their lines split. That makes sense, or did I just totally throw in something that's not necessary? All right, we'll come back to that. We'll come back to that. Ignore that. I didn't even say it. I was supposed to be motivation, not motivating. Okay.
It motivated me.
We talked a little bit about torque in the context of dipole moments. So let's talk about it in the context of magnetic moments. Okay. What does it look like? Me is the first letter. That one's good. Something cross something. Very good. I like that. Okay, that's the right energy. What?
R.
B. B. I want B. Okay, good. We're just gonna guess it out. No. What? So P would be your electric.
It's a magnetic.
It's a magnetic dipole moment, so it should be
Little M.
M. Good. Hey, we did it. We just derived the physics. No, I'm just kidding. All right. So let's think about what this means in practice. This is like our electric dipole moment, QB, and this would be our electric field, and the cross product of them would be the torque felt on the object, right? So here what I'm saying is the B field is going to do the same thing. I'm just saying this, right? The magnetic moment crossed with B is going to give you a torque on the material. You just accept that, okay?
Isn't it super similar to the dipole?
Yeah. We're going to treat them exactly the same. We're going to see that they are different, right? We're going to treat them the same. Okay.
What was the little M again?
This is our magnetic. M for magnetic. Dipole moment. Okay. Let's put something. All right, so let's put something like that, the this object here, and this B here. So what's gonna happen? You have an atom free to move. Yeah, you tell me how. Yeah, it's already spinning like that.
Oh, around the B field.
So let's say it doesn't move. Let's say the whole atom is not free to move up and down. But notice the orientation of the orbit.
Wait, what's not for you? Plus and the minus?
So the plus, the minus is obviously not good. Okay, let's say you have a very heavy atom. Okay, and you have a magnetic field, and the magnetic field is aligned like this, like my arm, like B here. Okay, and now I have an E, which is going around this way. Okay, for charge that's going around negative like this. Okay, and the B field is going like this, sideways. What is the torque or force that is felt by that electric charge?
You mean like or just like?
Conceptually, let's think about it, right? We started at the very beginning of class, we had this force law about B fields and everything else.
It's also that even like class B, talking about like the UV cross creates it. That's
Right. Yeah, so that would be the force, right? So the force would be V cross B, right?
Oh, yeah.
Would it be or not? Because moving charges, they feel the Lorentz force. Non-moving charges, they're not going to feel anything from B. Okay, so B is this way, and V is this way. So you tell me which way is the force. Okay, I'm moving this way right now. Okay, how do I do my right hand rules? Oh no. Okay, we'll walk us through it.
Wait, what did you say?
I don't know. You tell me. You stuck your finger out like this. What does it read?
If you're facing this way.
Yeah.
And then.
At this moment here, the electron, as it's going around in its orbit, right, like this.
Yeah, so we kind of like forcing you.
So how do you show me how to orient my hand? So this is V, Okay.
And then as we.
As B. Okay, the force is out.
Yeah.
Okay, and then it goes over like this.
Yeah.
No, because this is
No.
B, right?
Now.
Okay. So it's like this. Is that right? Let's see if that's right. So it's like that.
So it's in a different area now.
Okay, and then backwards like this way. I have V. Oh yeah. Is that helpful? Okay, V, E, now it's down again, the opposite there. And then on this side, going backwards.
It's like,
Yeah. What equation were you using?
We're using the right hand rule to look at the forces.
What was the cross product?
Trusty.
V cross V, right? Does it feel equal force everywhere? No, it's not. There's gonna be orientations in which the force, the velocity and the B field are not, they're parallel, right? And V cross B, when they're parallel, means zero. Good. Okay, you need them crossed. Okay, so when they're here and they're like this, right? That's a good cross. When they're over like this, it's smaller. When they're like this, it's a good cross again, the opposite way. No, when it's like this, they're small, right? Okay. The orientation of that is always changing. Okay, and we can work out the math. But essentially, you're gonna have something that acts like a dipole moment. Okay, and as this thing goes around, which direction will the dipole moment be? How's it gonna want to align itself? With the field. Yeah. So it'll go like this. Because if we think about let's make the B field up and down now. Okay. Going around in a circle. Going around in a circle. Okay. If you're not aligned with the B field here, so here's B up and down, and as you move around in a current circle, right? That's generating B in the same direction. Okay.
So how would it align? How would the dipole align?
So you go from this orientation, right? To that.
Oh,
Yeah.
okay. So it goes perpendicular to.
What do you mean? The face of the current charge,
Yeah.
right, will have a normal to it. That is your M direction,
Okay.
right? And so you go like this.
Okay.
And you're noticing something already, right? You have some external B. It's going to
That's why they all,
tilt.
that's why when a metal is scrambled, when you put a B field to it, they all orient and then it's like this.
Right?
God damn.
Okay, so that is an example of paramagnetic, because we have the dipole moment aligned. Right? I haven't told you about diamagnetism yet. Okay. What is the force? Shit, I'm absolutely out of time. That's okay. So we had this fun picture. Here is the way that it actually looks. Here's B. Here's M at some angle. Here is the normal. And then here's the force. Okay. So let's say this is the charge, E minus. Does that make sense? That's the same picture. Okay, the force that you feel for a non-uniform field is this fun thing. This is the magnetic moment. This is the B field. You dot them, and you take the gradient. Look how many fun vectors there are. Okay. This one's unique because in addition to rotating it, it moves the whole thing. So before we would put something with a polarizable vector, right, into an electric field, and it would just rotate it because you had an equal and opposite charge. But as you'll notice here, and maybe I'll have you work on this in the homework, you can get it simple stuff too. Okay. So diamagnetism, this one here, the orbital speed of the electron becomes altered. Right? And this is a property of the material. We're not going to get into this because I don't like materials. So I'm just going to tell you that this is true. You don't have to ask any questions. This creates a dipole moment of the opposite field. Whereas paramagnetism, we kind of saw that already. Unparalleled has spin, torques to have it line up with B. This was an example that we can actually think about. This one. Okay, both of them are small moments. Magnetic moments are not as strong as the polarizability moments. So when we have, for example, water that's running down and I charge up a little rod and then I put it next to it, you see that's a big effect. You tend to see the magnetic effects in your life much less. Okay. I'll also add these come from even electron counts, and these are odd electrons. This is why we're talking about this one. This one here, they misalign, and then they create an opposite field. Shit, we're running out of time. Okay, before I jump into this, do we feel okay with this idea? Okay. I'll just say that, you know, we're talking about this in the context of a uniform field. In a non-uniform field, this is the force that acts to move the dipole, M cross B. And right, you could write this out as a Taylor expansion. You could think about the individual terms. I think that's worth it for this class, right? Okay. We're not going to do the example here, but I do strongly recommend, right? We did a bunch of brand new stuff here, all the magnetostatics, the Fields of Art law. Let's recap those, reread chapter, I think 5 for magnetostatics, and then jump into 6. We'll talk a lot more about essentially what it looks like in a real material. So I would say Tuesday's class will be fairly conceptual, where we'll use the ideas of individual magnetic moments, how we go from individual moments to the material as a whole, and what does it mean to have magnetization, the big M. Right, so before we did little p, big P, we're gonna go little m, big M. Right? Okay. Questions? Okay, thanks, folks.
Are we talking about, so